Today we will conclude lesson 5.4, logarithms and the logarithmic function. We will look at questions relating to converting exponential expression to log form. We evaluate logarithm and use benchmark to estimate the value of a log and identify the characteristics of a graph of a log function. Just a reminder, the key concept, the log function is the inverse of the exponential function, and the graphs of the log function and exponential functions are related. Just to show you just the overall view, let's go back to our, it says that the log function is the inverse of an exponential function. So here's your exponential function, the log is the inverse of it. And if you were to compare log 3 to the x, so 3 or y equal 3 to the x, this is the shape you'll have. And these are the characteristics of the exponential function. And these are non-transformed. Later on, we will look at transformation of the log. We already looked at the transformation of the exponential function. So the first review question is, what is a log? Explain what log 5 to the 25 means. Now, a log is an exponent, basically what it is. It's an exponent. So, for example, let's be log 5 to 25. This would be equal to 2. So it's an exponent, right? So if you have this log 5 to 25 is equal to 2. This is the log. This is log 5 of 25 is equal to 2, which is the exponent of 5 to the power 2. So that's why we say that we can say a log is an exponent. Okay. Now, what does log 5 to 25 means? So log 5 to 25. This is the exponent of the power of which 5 is raised to give 25. So this is equal to 2. So it is the exponent of which 5 is raised to give 25. So this is the exponent of the power, oops, in this case, the exponent will be 2. We'll find it out. This exponent of the power to which 5 is raised to get, here we have it here, 25. So we can say that is, and we can conclude log 5 to the 25 is equal to 2. So log is an exponent, and it's what is the exponent of which a power is raised to give that value. Okay, let's look at evaluating the logarithm. And here are a couple of questions I'm going to work through here. Here we have log. We want to find what is the exponent, as we just mentioned, right? The log here is an exponent. So we want to find what is the exponent that I must raise 4 to give me 16. Okay. So remember our, we know this fact b to the bn is equal to n. So that gives us our exponent. So if I could write 16, right, using 4 as the power right, 16 is a power of 4, we can say that log 4 to the power 2, because 16 is 4 to the power 2. So now it's equal to 2. So we can conclude log 4 to the 16 is equal to 2. Of course, log 4 to the 16 is the exponent 2. So essentially, I'm taking 16 and writing it as a power of 4. I can make a note here. So write 16 as a power of 4. And that applies to any log where you have a base. Now, this is a little bit tricky one because when no base is given here, it's understood to be 10. This is standard. So if you see a question when there's no base, it demands that by default it's 10. Because it's so commonly used. Engineers love this value. And we see that. So essentially this is going to be like log 10 to the 100,000. What you like to do now is to write 100,000 as a power of 10. So 10, how much? 1, 2, 3, 4, 5. 10 to the power of 5 is equal to 100,000. So we have log 10 to 10 to the power of 5 is equal to 5. So the answer is equal to 5. So log 10 to the 100,000 is equal to 5. Okay, the same principle will apply here. We have now write 1296 to the power of 6. So we have log 6. Now these 6, how many times 6 can multiply? Give us what, 4? And the answer is 4. So log 6 to 1296 is equal to 4. So log 1296 is 4. Because 6 to the power of 4 will give me is 1296. Now, here we already have a base. This could be exponent of 1. So now we can rewrite it as log 2 to the 2 to the power 1 is equal to 1. So therefore we say it's 1. Let's recall, as long as we have the 2 in this case, it can be written as 2 to the power 1. And so therefore, that will be the exponent. In other words, 2 to the power 1 is equal to 2. So if we put 1 here, 2 to the power 1 is equal to 2. Now we now change, we'll write this now as an exponential, as a log expression. And remember, when we're writing these, this is our exponent. Now that's your, remember we said a log is exponent. So the equal, this is your base. So this is your exponent, their log answer. So equals 6. So we can put that here. So it'd be log, your base is 2 to 64. So remember that. So we have your base. Now the base for the exponential and the log are the same. And what they are equal to is the exponent. The log is equal to the exponent of the exponential function. So log 2 to the 64 is equal to 6. So we can say the base is 6. Sorry, the base is 2. And the log 6 because it's the exponent, which is the exponent. This would be similar. The base is 10. The log is equal to 4. So we say log 10 to the 10,000 is equal to 4. Let's recall in the second example here, the base wasn't written because it's base 10. So sometimes you'll see you don't have to write it because it's base 10. You can write it as log 1000 equal 4. There is a 10 here, but by convention it's not written. Okay, we're we'll do the reverse and write this again. And there's some more practice questions. Here we are using again our principle of adjustment. Y is equal to a to the x, which is log a to the y is equal to x. So now we want to change this into an exponential. So now this is our base. This is our exponent. So this gives me, so the base is equal to 7. Exponent is equal to 5. So it becomes 7 to the power of 5 is equal to 16,807. This of base equals 9. Exponent is equal to a half. So this becomes 9 to the power half is equal to 3. As I mentioned, if its base is written, it means 10. So in this case, the base is 10. The exponent is negative 2. It's negative 2 here. So we'll have 10 to the negative 2 is equal to 0.01. This is base. This is your exponent. So base equals 3. Exponent equals negative a half. So 3 to the negative a half is equal to root 3 over 3. Now we are using benchmark to estimate the value of log 5 to the 100. Because we cannot write 100 as a power of 5, we have to use benchmarks. Because you cannot write, so cannot write 100 as a power of 5. So we have now, as so we have to estimate. We have to estimate the log. First thing you want to do is 100. So we try 5 to the power of 2. Now this is by trial and error. Okay. 5 to the power of 2 is 25. Then try. Now that's not close to 100, but let's try now 5 to the power of 3. And that will give us 125. Now, 100 is closer to 125 than 25. So we will not use 5 to the power of 2 because 100 is much farther away. So 100 is only 25 away from 125 compared to 75 away. So since 100 is closer to 125, use 5 to the power of 3. So we can conclude that log 5 to 100 is between 3 and 2, but it's much closer to 3 than 2. So what we do now, we're going to try 5 now. So we have 5. So we're going to try 5.3. So we try 5 to the 3 point. Now this will give us way above 125, so that will not work. So we have to go smaller than 5.3. So we try 5 to 2.9. Let's try 5. So this will give us, okay, let's redo this here. So 5.3 will give us 125, which is way above 100. So we have to go lower to 2.9. So if you try 5 to try, let's see what will we get here. So 5 to the 2.9, 106. So that's above 106.41. Now let's try 5 to the 2.8. Which is 90.59. Now, if you look at the 2 here, 2.8 and 2.9, 5 to 2.9 is 6.41 away from 100. And 90.59 is 9.41 away from 100. So this is closer. So 106.41 is closer. So we can say here 5 to 2.9, which is equal to 106.41, and 5 to 2.8 is 90.59. This is closer to 100 than this. So we can conclude log 5 to the 100 is equal to 2.9. So it's by trial and error. So you benchmark, and then you try different exponent to see which one is closer than what's given in the log. And here we are using our principal log b to the bn is equal to n. So we're going to convert our 8 as a power of 4. So 8 is equal to, now this could be written as 2 to the power of 3 because there's nothing there for. But remember, we know from previous example that 2 can be written as the square root of 4. So we're going to change this guy to square root of 4. So it's a 2 to the power of 3 is equal to, we're going to change this here. This becomes the square root of 4 to the power of 3. This is really, I'm replacing 2 with the square root of 4. Now, if we write this as an exponent, it becomes 4 to the power half, power 3. So 4 half, because it's, which gives me 4 to the 3 over 2. So now I replace 8 with 4 to the 3 over 2. So we see log 4. I'll just rewrite it here. And we get this, which is log 4 to the 4, 3, 2, which is equal to 3 over 2. You'll see questions like these given regularly. Just be careful with your results. So we can conclude, write it underneath here. 3 over 2 is equal to 3 over 2. Here we want to write 27 is a power of 9. So what you want to do here is to write this as, so 1 over 27 could be written as 1 over 3 to the power 3. And we apply the same principle as we did over on the previous question before. We're going to convert this 4. We're going to write this 3, as 3 in another form. In this case, we write it as 9. Same as how we wrote the 2 as the square root of 4. We will do the same thing here. Let's work this through. Now, 1 over 27 now is equal to 3 to the negative 3. Now, so I'm going to replace 1 over 27. So we have log 9 is 3 to the negative 3. Now, we need the same base here, same value here, because our principle applies. This has to be the same. The power has to be the same. So now we can write this 3. So 3 can be written as the square root of 9. And that's how we get around that. So what we'll do now, this becomes square root of 9. So we have log 9 is square root of 9 negative 3. I'm just replacing this 3 by square root of 9. Now, square root of 9 is the same as 9 half. So now I'm going to replace this. So we have log 9. We have square root of 9, replace 9 half. Remember, we're using our rules as the power rule, or in this case, we use the fractional exponent rule. So the fractional exponent rule we are applying here. Just remember the fractional exponent rule that if we have x to the a to the power, let's do y here, our answer is a is y over x. That's our fractional exponent rule. That's what I'm applying here. So now I can conclude it's equal to, now we have to multiply these two now using what we call the power rule. We use the power rule. So let's work this through. So half times -3 gives me -3 over 2. So my answer is -3 over 2. So log 9 to 127 is equal to -3 over 2. Here we have question statement. Describe the relationship between the function y equal log b to the x, where b is greater than 0 and b is not equal to 1, x equal to 1, y. In other words, describe a difference between a log function and an exponential function, and sketch a graph of each function and list its characteristics. So the log functions, we can say here, the log function y equal to log b to the x. It is the inverse, and we looked at it at the beginning, is the inverse of the exponential function. The exponential function y equal b to the x. So it's the inverse of that. So we can, and that's because, to put another way, the graph of each function is a reflection of the other in the line y equal x. Okay, let me explain that. Now here we have exponential function. And this is your logarithmic function. The log is a reflection. So remember this point here is 0, 1. If you switch these around, it becomes 1, 0. So by switching them or exchange them, it shows you it's a mirror of each other. Now, what do you mean by that? If I were to draw a line here, and this is y equal x, the slope is 1, the y-intercept is 0, the perpendicular distance from one point to the next will be equal. Distance from here to here is the same, because they are a mirror reflection of each other. So that's why we can conclude that they are inverse of each other. So the exponential function is the inverse of the log function. And we know from the characteristics before, the log function, the x-intercept is at 1. The y-intercept, there's no y-intercept, the log function, because it's an asymptote here where x equals 0. And the domain is from 0 to infinity, and the range is from negative infinity to positive infinity, or all the real numbers. The reverse is for the exponential function. There's none. Notice there's just reversing and the real numbers. So that's why we can say it's a mirror reflection of each other. We conclude with one last question, looking at graphing a log function. And here, we want to graph log 4x. The easiest way to do this question is to write the inverse of log 4 to the x and determine the value and interchange them. So in other words, we're going to say the inverse. Oops, let's put this a problem here. So write the inverse of y is equal to log 4x, which is y is equal to 4 to the power x. And what we'll do next is to determine, oops, here we go, losing my track here. Once we have our exponential, so in other words, exponential, and we know the exponential is a reflection of the log, determine the values for the exponential, y is equal to 4 to the x, and interchange them. And then interchange, in other words, just switch them. And interchange the coordinates of the table. Of the values for y is equal to log 4 to the x. So in essence, what we're doing, we're creating two table values, one for y, for the x, and then we switch those values. And that will give us our coordinates or the table of values for log 4 to the x. So let's go ahead creating a chart, a table of values. So I'm going to do that here. So this is y is equal to 4 to the power x is so exponential. So x, and this give me y, which is equal to 4 to the power x. Let's start with -2 here. -1, 0, 1, and 2. So 4 to the -2, which is 1/16. 4 -1 is 1/4. 4 to the power 0 is 1. 4 to the 1 is 4. And 4 to the 2 is equal to 16. So now for y is equal to log 4 to the x, we just switch these two now. The x and y. So y is equal to log 4 to the x. Now 1/16, now we interchange them, -2. Then we have 1/4, give us -1, switch these here. Then 1, 0, 4, 1, and 16, 2. So now we have our coordinates for the graph. By the way, you can go ahead and sketch both of these and you'll see it's a reflection. I will just sketch a graph for one of these. So I'm going to have my x and y coordinates here. This is my y. So here we're okay, 2, 4, 6, 8, 10, 12. We're going 18. Here, -1, -2, -3, 1, 2. The first one, x is 1/16, -2, which is about here. A quarter is -1. 1, 0, which is about here. This is 1. That's 2, 4, going up by 2. The next one before 1, here. Next 16, 2. If we were to go on at 32, if you can add this, this will be 32, 3. See, that would be 64, sorry, 64. This would be 64 because they're going up by 4. So this is a multiple of 4, going up by 4. So 16 times 4, 64. And if you can continue this if you want, times 4, going to give me what? 64 times 4, 56, etc. You could also find it from here. If I were to go back to my original graph, and I have 3 here. So 4 to the power 3 gives me a 64. And 4 to the power 4. Now will that give us 4 to the power 4, 256. So we can do this 256 because it's going up 4. It is going up 4 times by 4 times the original amount. And that can tell you if it's an exponential function. There is a constant how many times it's a multiple of itself. If it was 2 times, it means that every time period is doubling. Or if it's 3 times, it would be tripling the scale. So now we connect our points. Oops, that's going to be, we have 2 here. This is log 4 to the x. Just a note, you could have bypassed this table of values and go straight into finding log 4 to the x. The challenge with that is that you'll have difficulty determining your x values. But one way to get around that, look at your base here, and then you will find factors, right? Powers of 4, or whatever your base is. If this was 2, you find powers of 2. So it can go up, is going up by 2. So you can use that. In this case, that's 4 would be 1/16. If it was 2, you probably will go on to, like, say, 1/4, etc. That's one way of getting around doing 2 tables.